Welcome to the Journey Chez Chem. Well, today's warm-up is a little bit of practice from yesterday, and then we're going to have a demonstration lab. I know you're excited. I'm excited. So please do the 2 warm-up questions to the best of your ability, and we'll discuss them in a moment. In number 1, we're determining the vapor pressure of a solution that contains potassium chlorate. And we have to change our potassium chlorate to moles because we're looking for the mole fraction of the solute to put into our formula. Well, potassium has an AMU of 39.1, and chlorine is 35.5. And 3 oxygens is 16.0 times 3. And then, of course, you know, I do the math again, and I add them all up, and I get 122.6 grams per mole for the potassium chlorate. And when I do the math here, I get 0.5301 moles of the potassium chlorate. Now, I also have to find the moles of the solvent, and I have 250 milliliters of water. And 1 milliliter of water is equal to 1 gram based on its density. And then I change my grams to moles. And I get 13.8888. And I add those 2 moles together to get the total number of moles. And that would be 14.4189 total moles. Now, then we have to look at the equation. And what we're going to do is find the change in the vapor pressure of the solvent is equal to the mole fraction of the solute times the pure vapor pressure of the solvent. Now, my mole fraction here is of the solute, so I take my 0.5301 is the moles of my solute, divided by the total moles, which is 14.4189, and I multiply that by the pure vapor pressure, and I have that on a chart, and the pure vapor pressure is 5.6 kPa. Now, this value may be given to you on the assessment, and because it's multiple choice, we need to make sure that we have it written in the proper form, and that would be 0.03676. 4 significant places past the decimal and cut it off. And when I multiply these 2 numbers together, I get the change for the solution's vapor pressure, and the change then is 0.2058. Vapor pressure goes down the more particles that we add. We originally had a 5.6 kPa, and therefore I take my 5.6 kPa and subtract the 0.2058, and I get a new vapor pressure of 5.3942. And then I go back to my original problem to determine how many significant digits should be in my answer. And I see it should be 2. And therefore the 9 rounds the 3 up, and I get 5.4 kPa for my solution. And that's how you do number 1. In number 2, we are determining a boiling point and freezing point for a solution. And we have 12.5 grams of lithium sulfide. And lithium has a +1 charge, and sulfur is -2. And we always know we have to get our compounds written correctly. Well, the formula that I'm using is that the change in the temperature of the freezing point is equal to the molality times the constant times the number of particles. Therefore, I need molality, so I'm going to change my grams to moles for my solute. 1 mole of lithium sulfide has a mass of 45.9 grams. And lithium's mass, there are 2 lithiums, And each lithium has a mass of 6.9. And sulfur is 32.1. And 6.9 times 2 is 13.8 plus 32.1. And I get 45.9 grams per mole. And then when I do this math here, I get 0.2723 moles of my solute. And then to get molality, I have to divide by the kilograms of solvent. Well, I have 300 milliliters of water. And 1 milliliter is equal to 1 gram. And 1 kilogram is 1,000 grams. And therefore, this denominator is equal to 0.3 kilograms. And then I go ahead and calculate this to get my molality, which is 0.9076 molal. And I'm going to use this in both of the equations. The only difference between this equation and the one for boiling point is that the constant refers to the boiling point of the solvent rather than the freezing point. But they're very similar here. Therefore, I have 0.9076, and the freezing point depression constant for water is 1.86. Oh, there's a molality here. Degrees Celsius per molal, and we have 3 particles, because when lithium is added to water, we get 2 lithiums, lithium sulfide I should say. I get 2 lithiums and 1 sulfide, which is a total of 3 particles. And when I do the math here, I get a change in the freezing point of 5.0644 degrees percent. Degrees Celsius. Now, water normally freezes at 0, and therefore the freezing point goes down, and I subtract the 5.0644. Now, freezing point, we're going to take normal significant digit rules here, and I'm going to get minus 5.0644. I look back to my original problem, and I see that I need 3 significant digits, and therefore my final answer is negative 5.06 degrees Celsius is my new freezing point. And the process is very similar to boiling point. And I'll go through that in a moment. Now we're solving for the new boiling point. Well, the formula is very similar to what we had before. And I needed the molality, and the molality was 0.09076 molal. And my constant for water for boiling point is 0.512 degrees Celsius per molal. 3, I'm just anxious to put that 3 in there. Per molal, and I have 3 particles. And when I multiply all this out, I get 1.3940. Now, water normally boils at 100 degrees Celsius, and boiling point goes up, and therefore we add 1.3940. And I get 101.3940. And I have a special rule for boiling, and we're going to take it 3 places after the decimal rounded, and therefore my final answer here is 101.394 degrees Celsius is my new boiling point. Now we have to do one more thing before we can have the demonstration. I need to talk to you about how we solve for molecular weight using freezing point or boiling point information, and I'll be right back. A very important concept that comes up many times on many different types of assessments is how to determine the molecular weight of a compound using these formulas for boiling point and freezing point depression and boiling point elevation. Well, whether I use the one equation for the boiling point or for the freezing point, it doesn't really matter because the process is the same. So I'm going to go ahead and use the freezing point because that's one that we often see. Now, first of all, we need to understand that most often, wherever I've seen this, is that we are given non-electrolytes, and therefore we do not have to worry about the Van Hoff factor and the number of particles, because it is always a non-electrolyte, and therefore it would only be multiplied by 1. Now, we know that molality, and I'm just going to go through the math to show you how we derive this equation. Molality is moles of solute per kilogram of solvent. And therefore, I just substituted that in. Now, I'm going to multiply by kilogram of solvent to get it out of the denominator. So I have kilogram of solvent times the change in the temperature of the freezing point is equal to the moles of the solute times the constant. Now, you'll remember what moles are. Moles are grams of solute per molecular weight. Grams over molecular weight is moles. And we still have our constant here. And we still have the kilograms of solvent times the change in temperature of the freezing point. Now, I'm going to rearrange this equation to get molecular weight out of the denominator and solve for molecular weight. And therefore, my molecular weight, or molecular mass, is equal to the grams of the solute times the constant divided by the kilograms of solvent times the change in temperature of the freezing point. Now, you could solve this if you needed to, if somehow you forgot that. Or oftentimes students just memorize this. They just like to memorize things. I don't know why. I'd prefer to solve it, but that's okay. You can do it however you like. So that's the equation for molecular weight. Now, the work that you need to do to practice this, you have one side of an example worksheet. There's only 3 problems there. And the other side, well, that's not going to be due for a few days because we're going to be doing a lab tomorrow as well. And I'm just so excited. I get to do a demonstration lab now, and then I get to do a lab tomorrow with you. Well, that's just great. And so here's how you solve for molecular weight. And I'll be right back to talk about that demonstration. Here we are. Now, you are going to need to write this up just like any other lab. You'll have to come up with your own title and objective and observe what I'm doing in order to write everything up. Now, what I have here is a 1-liter beaker, and I have put rock salt in this and icy water, lots of ice and lots of water, in order to lower the freezing point of the water. Well, I also have a bottle of club soda here. And the club soda is just carbonated water. And therefore, we have carbon dioxide as a solute and water as a solvent in the bottle. Well, we also have a solution here as well of the icy water, and the rock salt is my solute in the beaker. And I was making sure with the thermometer that I was getting my temperature low enough. And now you need to make an observation. Are you ready? Here we go. Wow, that's just crazy. Well, what happened was, when I open the bottle, the carbon dioxide can come out. And therefore, as it comes out, my concentration of the solute that's in there is less. And therefore, the freezing point comes up. Isn't that cool? I had a great time doing that. And that's the demonstration for today. And now you get to write it up, and I know you'll have fun doing that. So, thanks for being here, and I can't wait to see you tomorrow. Bye!